So this webinar is supported by the Engineering in Medicine and Biology chapter of the Czechoslovakia section of IEEE, as well as this webinar is also supported by the International Union of Radio Science. And today is my great pleasure to welcome Professor Sunao Katsuki in our webinar. And I would like to briefly introduce him because he's a quite interesting experience in this field of today's webinar. He received his PhD, a doctorate in engineering from Kumamoto University. And then, interestingly, he also joined the nuclear fusion research in Germany for a year. Then he stayed with the Schönbach lab in Albumin University in USA. And also since the time he started the biological application of pulsed power, particularly in the field of bioelectrics. And currently his strongest interests are in ion transport and also through the permeabilized membranes, and also through the effects his interests are also on the pulse electric field effects on biomolecules, which is also our great interest too, and also in applications of these technologies. So without further ado, I would like to ask Dr. Katsuki to start his talk. Please, the screen and the voice is yours.
Okay. Thank you. Thank you for kind introduction. And thank you for inviting very interesting the bioelectrodynamics webinar as a speaker. So I'm Sunao Katsuki of Kumamoto University, Japan, and I'm gonna share the slide first. Okay. Oops. No, maybe no. This is not good. Well, こっちか。シェアで。Alright. これだね。共有停止して。これか。デスクトップウィンドウこっちだ。よし。OK。Oh, no. This is not. So. ウィンドウ、これか。デスクトップ、ウィンドウ、デスクトップか。OK。Alright. Okay. Okay. So my slide. You can see my slide correctly?
Yes, we do. It's perfect.
Okay. All right. So I'm gonna start my talk about the experimental study of proteins exposed to intense pulse electric fields. Okay, I'm now belong to Institute of Industrial Nanomaterials. This is one of 3 institutes in Kumamoto University, Research Institute in Kumamoto University. All right. Okay, so today I'm going to talk about the bioelectric study at Kumamoto University, and I think next I'd like to talk about the pulse power generator. It's a technology part, how to build the pulse power, and the next I talk a little bit about the protein exposed to intense electrical pulses. We are now trying to analyze the proteins in several ways. So I'm going to show what we are doing, and so finally I summarize. Okay, before going to the research part, I'd like to introduce the Kumamoto and our university. Here is the Kumamoto. Okay, I'm going to show. It's Japan. It's almost a 2,000 kilometer length from Okinawa to Sapporo, northern islands. And here is Korea and China, and Beijing is here. Now Olympic is going on. And here is the Kumamoto is located in the Kyushu Islands in Japan and rich in nature. We have the large volcanic assault mountains, and in the eastern part of Kumamoto, and in the west, there is a Amakusa seashore with small islands connected by 5 bridges. And Kumamoto cities, where historic Kumamoto Castle is surrounded by the trees here. And we have the water springs, and we can drink directly through the come from the underground. And we have the nice onsen hot spring around just within hour from Kumamoto City. Here, the Kumamoto University is not a big university, but this is one of the 86 Japanese national university. We have 7 faculties, 9 graduate schools, and 25 research centers and institutes. The number of students is 8,000 for undergraduate and 2,000 for graduate. And okay. Here's the pulse power group in Kumamoto University. I think a relatively big group for pulse power research. And I and Professor Hamid Hosano and Professor Yano Kenichi is working together on the bioelectrics research. And the pulse power engineering part, the Professor Sakugawa is working and he's doing a good job. And also we are working on the environmental and agricultural applications of pulse power. Professor Takao Namihira and Duyan Wang is working on that. And former the professor who established this laboratory, Hidenori Akiyama, is already retired, but he's running his own company, private company. And we have technologies to build the pulse power generator by ourselves, and the variety kinds of pulse power generator you can see. It's a magnetically pulsed compression generator and IGBT MOSFET driven pulse generator, of course, and also spark gap driven Marx generator. It's a conventional pulse power. And also we have modern MOSFET driven Marx generator here. It's driven 200 Hertz, and this provides 20 kV and 2 kiloampere high power to food applications. And I'm going to talk later about the 1 nanosec Marx generator. It provides 200 kilovolts for 50 ohm loads. And also we use spark gap driven Bloomline pulsar, which provides 30 kV 5 nanosecond to the 10 ohm loads. And the right hand side, you can see this is just it's a combination of the products. It provides AC pulse generator. The amplitude is not big, but 1.2 kV, and the frequency range from 0.2 to 100 megahertz. Okay. Anyway, this is one of the example we have, but anyway, we have a technology to to build pulse power generator by themselves. And here's just one example of the pulse waveform we use. Okay. I talk today a little bit about the 1 nanosecond pulse, 200 kV pulse generator here. And okay. Okay. Here is what the facilities we have. But okay, I skip this one. It's a all right. And now I'm interested in the many things, and based on the pulse electric field effect on the biological cell. The major impact of the pulse electric field is membrane permeabilization, and which can be used for sterilization of liquid foods and liquid medicine, and also the extraction. It can be used for extraction from the potato or sugar beet or something like that. And also this can be used for food processing and the extraction of the enzyme or DNA or something like that from the cell. And we used to worked on that medical application, but now I cannot afford to do this one. Maybe in future we restart the medical application of pulse power. Anyway, this application is based on the primary impact of the pulse electric field, and also okay. Here that okay, when we apply the pulse electric field into the biological cell, many things happens, of course, and however, the first impact is important. I'm very interested in the first impact, primary impact of the pulse power to a biological cell. And this primary impact can be the membrane permeabilization because of the field enhancement of the membrane. The enhancement field reached to more than megavolt per centimeter. It is pretty big. And also these proteins and DNA, the high electric field affects on the proteins, the DNA. However, especially the field enhancement occurs at the membranes. So membrane proteins should be affected by the high enhanced electric field. There also the primary pulse electric field can be used for rapid heating of the media. For example, within millisecond, you can raise the temperature of the biological target tens of degree. They increase the temperature within a millisecond. So this is a primary impact, and of course, after the primary impact, the secondary, the physiological process is going on. Then finally, something happens as microscopic behavior. Okay, but anyway, I'm interested in these secondary processes, but I cannot do this, and I gave up working on these secondary processes. And now I'm focusing on the primary impact. of the parasitic field, especially on the membrane permeabilization and the proteins. Okay, let's skip this one. Okay. I'm going to show you one of the example of the how pulse electric field work on the cell membranes. This is one the fluorescent microscopy, and we have micro electrodes, microgap electrodes under the microscope, and we can see what happens in time when we apply the pulse. But we can provide any kind of pulses to the electrodes. So the typical gap distance of this electrode is 200 micrometer or more. Here you can see what happens in the cell. This is an artificial cell, and when we apply the electrical pulse in the transverse direction, here, so you can see something happens in this membrane. Here also, because the membrane lipid is fluid, so in this stress that membrane density, lipid density, it changes after the deformation. You can see that. And when we increase the field strength, so what happens here? When we increase the 10 times higher, so you can see that of course the deformation occurs, but this cannot move in the original shape. So you can see that the membrane, the break like this. Also, you can see very interesting when we apply the 100 nanosecond pulse duration, but we need a higher electric field. Here you can see there is a too short for deform because of the pulse is short, too short. However, membrane is permeabilized, so you can see something flow into and flow out through the membrane, permeabilize the membrane. So you can see that the stress to the membrane strongly depends on what kind of pulse you applied to the cell. Right. Okay. And here you can see that the special setup for to see the real membrane hole pore that we assemble the membrane flat single layer membrane on the very flat crystal. Then we apply the pulse. Then you can see that the black spots on the membrane here, that this is the black spot is pore. And when we apply the 10 microsecond pulse, microsecond range, the pore is formed on the membranes. However, when we the pulse duration down to 150 nanosecond, it's very small pores. It's only small pore is formed here. However, when we use the atomic force microscope image, a microscope, you can see many spots on the membranes. So this the image clearly show that the pore, the formation depends on the pulse shape or pulse duration. Okay. And here is this, or this is also movie. And of course, once the membrane is permeabilized, the intracellular molecules flow out through the membrane, and also extracellular molecules flow into. So this the movie showed that all right. Oh, unfortunately, I cannot show you here. Oops. Oh. Anyway, when we apply the pulse, and the extracellular ions flow in, and the intracellular substances flows out, and this time constant is in the millisecond range. Here you can see also this flow dynamics depends on the what kind of the pulse you apply to the cell. For example, the 10 microsecond and relatively small electric field, you can green shows calcium ion, intracellular calcium ions. So this indicates that the extracellular calcium ion flow into the cell through the membrane here. However, when you use 20 nanosecond 100 kV per centimeter, the calcium emerges from just surrounding the nucleus, not through the membrane. Just calcium emerges from the inside organelles. And when we use 500 nanosecond, just between 10 microsecond and 20 nanosecond, and amplitude is also just middle between 4 kilovolt per centimeter to 100 kilovolt per centimeter, just middle pulse. You can see here the both phenomena simultaneously occurs. You can see here the cell membrane, and it shows the green fluorescent, and also the nucleus, the edge shows the green fluorescent, right? So the 500 nanosecond have both effect of 10 microsecond pulse and 20 nanosecond pulse. Okay, so anyway, this is the things happens when we apply the pulse to the cell. This is mammalian cell. But I think the today the people in joining this seminar is interested in how pulse electric field work on the biomolecules, like such as proteins and DNA. So I'm going to move to the things related to the protein study. So as I said, the electric field, when we apply the pulse external electric field, the field is enhanced on the membrane because of the ion accumulation. So the field strength as the membrane exceeds the 10,000 kilovolt per centimeter. It's a megavolt per centimeter. So this membrane contains many kinds of the the proteins, membrane proteins. So these membrane proteins are sensors and transporters and many functions. So when the membrane protein is exposed to such a strong field, something happens. However, as I showed you before, the ion flow is the biggest event when a pulse electric field is applied to the cell. So I think it's difficult to detect what happens in the proteins. So I decided to build the very high voltage pulse generator to apply the macroscopic electric field on the protein. So, this is the Michel's work. I think that the Michel is working the many things on the proteins, how the electric field work on the proteins. Yeah, I always stimulated by your work, and I'm always looking at what you are interested in. And okay, now this is I think I don't think I should spend time for this because everybody knows this. However, I'm very interested in how the external electric field work on the hierarchical structures of protein, the primary, secondary, tertiary, and quaternary structures. Okay, so this is our first experiment using 5 nanosecond, 300 nanosecond, 300 kV per centimeter pulses. This is a maximum electric field we produced maybe 5 years ago. And this is a device we built, and we used a 1 millimeter cubit. However, okay. And this is Bloom line generator based on the transmission line theory, and that this Bloom line generator provides 5 nanosecond 30 kV pulses to a 1 millimeter cubit. And we use protein solutions in the cubit. Then we obtained the 300 kV per centimeter for that. But I think everyone knows that the cubit, it's easy to break down between the electrodes in the cubit. I think usually at most 30 kV is when you apply the 30 kV into the cubit, the breakdown easily occurs. When you use the microsecond pulse, however, we decrease the pulse duration to avoid the breakdown. And we did several things to avoid the breakdown between the in the cubit. Here is the Bloom line generator. Also, here is the driving circuit for the Bloom line generator. And this Bloom line generator driven by a spark gap switch here. And this is a charging circuit. And the system was operated at 3 pulses per second. And okay. And all right. we monitor the temperature when we operate this system at 3 pps. The temperature increase is just below 3 degree, and pH didn't change at all in this experiment. Okay, and we used the 3 kinds of proteins, a different shape, different character. Lysozyme and albumin and urease. And here you can see the molecular size, they're pretty different. Because we wanted to 1 megavolt per centimeter at that time, but we only have 300 kV per centimeter. We were looking for very soft proteins, materials, because we need to see the breakage of the or deformation of the protein. So the urease is a very good target for our research, our purpose. And also we use albumin and lysozyme for the comparison. And here the urease is very big and hexamer, and we can say the urease is a very soft material. So we expected the urease can be destroyed or deformed by the 300 kV pulses. And we analyze the protein formation using the electrophoresis. And after the exposure to PEF, we did several things for the electrophoresis. And the key thing is here, that treatment temperature and the duration. The combination of 70 degree centigrade and 2 minutes was selected to high order structure left in the protein. Usually, SDS treatment uses 95 degree for 5 minutes. So in that case, everything is dissolved and go to the monomer, single strand, the proteins. Okay. Here, the pretreatment to see a quaternary structure. Here, the electrophoresis, and here is the urease, the electrophoresis pattern. Here is a monomer band, subunit band, and here is a trimer band. So when you increase the pretreatment energy, the treatment temperature and the treatment time, you can see that the trimer band dissolved and turned into monomer. So we wanted to see the high order structure. So we use relatively low energy treatment conditions to have a trimer band in the sample. Okay. Okay, first I'd like to show the result of lysozyme and albumin. There actually, we don't see any changes by pulse electric field application of the 300 kV per centimeter. There's no changes, difference after the pulse applications. Okay, so this is a urease. Here you can see that there's something changes when we apply the 200 kV per centimeter. this number shows the electric field strength. Here, this is a trimer bands. You can see here that the band position changes. Also, subunit band, and you can see some somewhere something is going to collapse. So, but I don't know what happens in this case. Or anyway, the something and the higher band, the structure is destroyed by the pulse electric field. Okay, and also we look at the enzyme activity. Okay, the urease is an enzyme that hydrolyzes urea into carbon dioxide and ammonium, and we use the urease enzyme activity kit provided by a bioassay system, and this kit enables to detect ammonium, which indicates the urease enzyme activity. Here you can see again the electrophoresis, the band changes as I show in the previous slides, and the 200 kV per centimeter, more than the electric field, more than 200 kV per centimeter. You can see the changes in the electrophoresis band, and also here the urease enzyme activity of urease. We couldn't see the activity changes in 200 kV per centimeter. However, 250 kV per centimeter, 300 kV per centimeter, they clearly show that clearly the deactivated the enzyme activity. Okay, so we decided to build a new pulse power generator, which provide much higher electric field. Here you can see this is basically Marx generator, 10-stage Marx generator here, and here is a pulse sharpening section which has a main gap switch and a tail cut switch to shorten the pulse. And here is a PEF exposure chamber here. And the chamber structure is shown here. And I think in this kind of experiments, the measurement is very important. And we have the experience to measure the nanosecond or sub-nanosecond range, the voltage and current. And here's the cross-sectional view of the exposure section. And here's the center high voltage electrode. Here's the housing as a grounded electrode. And here, the yellow section is protein, that load section. And the gap distance is 1 millimeter. And these electrodes are coated by platinum to reduce the electrochemical interaction with protein. Okay, and here it shows the pulse sharpening section. Here's this blue part is connected to the Marx generator, and this pink part is the other electrode goes to connected to the exposure chamber. And here this blue part and this red part produces a capacitor, and that is this capacitor. It's to shorten the pulse rise time and to deliver the load. And the blue rod is inserted from the outside, and this blue rod is connected to the ground, and this main pulse, after main pulse goes to the rod, this gap is closed to cut the tail. And this housing is pressurized by the SF6 gas to prevent, to hold a high voltage. Here you can see the voltage waveform at the different positions. The lower the voltage is just the output voltage of the Marx generator, and the middle, the waveform shows the pulse provided to the exposure chamber without tail cut switch. And the top waveform shows the 1 nanosecond pulse to the exposure chamber here. Okay. And also, we are very carefully looking at the chemical species generated by the pulse. And of course, the hydrogen peroxide is generated by the pulse because of the electrochemical interaction between the electrode and the liquid. That we measures the hydrogen peroxide concentration of the liquid. And here is the pulse number, and here's the H2O concentration. And the concentration is increased with increasing the pulse number, as you can see here. Saturation level is 2000 micromolar. However, our experimental range is here. Just we use 20 pulses. Most cases, mostly 10 pulses. We can, 10 pulses is enough to see what happens in the proteins. And here, that the result that is the flow electron. So we need to check the chemical effect on proteins. Okay. Oh. Yeah, now we are trying to use several kinds of the measurement tool, the CD, spectrum, and the NMR, and SH group analysis. We have several good data, but well, we need to double check to see. Okay, so any question?
So is it okay? So that's on end of your slides for today.
Oh yes, yes.
Okay.
Yeah, actually, this is the last slides.
Okay, so go ahead, and then tell me when you are finished, and we will start the discussion.
Okay. Anyway, I have to say that the 3 years ago, 5 years ago, we used to use the 300 kV pulse. Only a few the proteins was broken. I mean, the deformed. But now we have 1.3 megavolt per centimeter pulsar. So that high field affects, many. For example, the albumin, we didn't see any changes in the 300 kV per centimeter. However, 1.3 megavolt per centimeter, something happens in the albumin. Yeah, also, there's some indication what something happens in the lysozyme and the myoglobin. I think, of course, we need to check the secondary or tertiary structures of these for using the CD spectrum and the NMR or whatever. However, I think we need to collaborate. Actually, we need to help. We need to help the theoretical analysis or understanding what happens in this. And also, we are just looking the irreversible the phenomena, the formation. However, I think it is interesting to see reversible deformation. I'm still looking for something, the way to find the reversible, the deformation and the pulse. Okay, and I think this CD spectra is this is the first data from the CD using the CD spectra for albumin. Well, this data shows clearly the secondary structure of albumin is affected by and changed by the exposure to the 1.3 megavolt per centimeter electric field. Okay. Yeah. As I said, I'm still it's the analysis of tertiary and quaternary structures ongoing. I'm doing the SH the group analysis of these several kinds of proteins, and now the last week I did the NMR for several kinds of proteins exposed to 1.3 megavolt per centimeter. Okay, maybe in future I will show you the results. Okay, right.
Okay. So thank you very much. Was it all from your slides? Then we can start this. I thank you very much. So clapping on distance, very interesting results. Again, I apologize for technical troubles, but I think, well, something we couldn't predict, and I hope we resolved that. I'm glad we resolved that, and we have the Dr. Sunao Katsuki back. So there are a couple of questions in the chat, and I'll just go as they appeared chronologically. So maybe I would like to give word to Anna Yulevna Bogdanova. If Anna, I will try to unmute you if you like, and you could try to ask the question yourself, because I think you had also had more than one. So let me allow Mike, and also I'll allow camera if you like. So Anna, if you like to ask questions yourself, you can go ahead. Otherwise, I'll read it.
Yeah. No, it's all great. I can ask the questions myself. So I was wondering about the mechanisms you think that affect tile groups, because you were talking about tile groups that respond to the radiation. And I wonder whether these are free radical-based reactions or protonation-deprotonation reactions that you engage when you irradiate your proteins. So that would be my first question. And the second question would be about heme-containing and heme-free proteins. And this is something obviously involving iron that might impact your responses, because you mentioned myoglobin. You may start with any of those.
Oh, okay. Maybe can you repeat the first question? Sorry.
Yes.
Yeah.
The first question is about the tile groups, SH groups.
Okay.
That you show respond to the field. And my question is, there are several chemistry reactions, chemical reactions that may be behind it. It may be the change in protonation of your SH group, so dissociation of protons or binding of protons, or it may be free radical based reactions when you get tile radical formed, and then you get the free radical based reactions. So what do you think is happening there, based on what you have seen?
Actually, many things. Yeah, it's possible to have. Actually, I have no idea.
Okay, that's good.
I have no idea.
No, I can tell you that we are going to study that with hemoglobins, hopefully. So we are going to get some ideas soon. I also don't have any idea. I just wondered, because we are new to the field, whether anyone else already got an idea about it.
Actually, of course, there is, the chemical free radicals, and of course, the pulse electric field. The people say free radicals happens such a high field.
Not necessarily. It may be water-based reactions. It may be proton-based reactions. So there are two possibilities I see. Maybe there are more. Okay. And what do you think about the iron of heme iron? How does it impact your responses? Do you see any differences between myoglobin responses and albumin responses or urease responses?
Heme?
Yeah.
So the question is the heme itself is stressed by pulse electric field?
Whether heme-containing proteins are more receptive to the field, whether they are more damaged or respond in any other way than the other proteins. Yeah.
Well, yes, there's it's a difficult question, that because we just started the analysis, chemical analysis, and actually we just collecting the data about the electrophoresis. So now we are just going to we are now studying the secondary structure, tertiary structure, so whatever. And maybe I think I need help.
Great.
I'm
a chemist. I like chemical side, but I'm not a physicist, and you're a great physicist with all these generators. So maybe we can talk about how to approach it. Because we are now developing protocols for that. So yes.
Actually,
But we don't have these great generators that you have. We have simpler ones.
I was expecting the collaborations or exchanges of opinions or
Okay.
Yeah. Good. Because our side is the engineering side, so it's a knowledge is limited. So
okay.
I can provide the device.
Fantastic. Great. Okay, let's do it together. Thank you. So yes, my email is somewhere in the chat. So I guess we can chat about it. Thank you.
Okay, that's great that we have these exchanges, and that's most satisfactory. We can see some corroboration arising from the webinars or conferences in general. So thank you, Anna, for the questions. I think we can if time remains, we can have some follow-up discussions. But I'd like to go through first to the questions we had.
Absolutely.
And Sunao said he should be finishing by past, so we have 12 more minutes. So there's a question from Noah Betzalel. If you like to ask yourself, I can. You are still there. It's also a question. Let me see in the participants. I don't see Noah anymore, but there was a question on seconds. Well, it was a question of which area or spot in the cells is affected by the pulse. That's more like a general question, like which area or spot in the cells are being affected in the pulse.
Of course, it depends on the pulse shape. When you use relatively long pulse, like a microsecond range or hundreds nanosecond range, I think that most pulse energy goes to a membrane. That results in membrane permeabilization.
Okay, thank you very much. Another question is from Johannes Benedict. If you are, let me check if you are still there. I can unmute you so you can ask yourself. Oh, I see. Let's allow Mike. So Johannes, you have the microphone allowed. I also can allow your camera if you like.
Yeah, thank you. Can you hear me?
Yes, we can.
Yes.
Yeah. Thank you for interesting presentation. So my question is more a little bit about temperature measurements and how you've determined the temperature with the setup, and eventually how many measurements per second have you been able to do? So I'm just wondering if you were able to resolve any temperature fluctuation due to the pulsing.
Okay. Of course, the temperature is very slow measurement. We don't have a fast measurement, transient temperature. Of course, now we are using the pulse with a very slow repetition rate. For example, the 1 pulse per second or something like that. So, of course, transiently, the temperature increases maybe 1 degree, 2 degree, or something like that. However, the heat is goes away in the big because liquid we are handling is very small, so heat is easily goes housing. So temperature, of course, the transiently increases just 1 or 2 degrees, but not big.
So increase. Do you think there's? I'm just wondering if there's certain amount of peak temperature values that could be reached at a maybe more local level when the E field is introduced. I understand it will be then distributed over time and absorbed by the apparatus, which is then at much lower. So I'm just wondering if there's certain effect that still due to temperatures, but we are just limited by our experimental setup. We just don't see it. We move to a domain where we just smear it out over time. And because the pulse repetition rate is so small, we see here only, you know, the average temperature rise, and which is small.
And also we calculate the energy, electrical energy deposited in the media. So, and of course, it's based on uniform energy dissipation in the liquid. However, if of course we are using the parallel electrodes, so we are expecting the uniform energy dissipation in the liquid. However, if not, maybe local temperature increase, transient local temperature increase happens in the media. Yeah. So, but okay, well, now I don't have an idea to see the such a local transient temperature, because pulse duration is 1 nanosecond. So I don't think we have
I was
too high. Okay.
I was facing similar problems. So I think one approach that we are trying to take now is to use reflectometry.
Okay.
To determine the changes in the dielectric coefficient of the liquid, which depends on temperature. And using some of the equipment that is available, you could achieve, well, we're achieving gigasamples per second. So we're maybe, not sub nanoseconds, but in the range of a few nanoseconds. So that I was wondering if there's maybe an option for you to consider. And also try to improve the separation between the E-field effect and temperature effect, which is very, very difficult, I guess.
Well, yeah, of course, yeah. However, yeah, at least maybe you can calculate estimate the maximum temperature from the energy deposition into the liquid. So in our calculation, the maximum temperature rise is just one. This is based on the 100% electrical energy goes to media because of the charge. It happens. However, even in that case, the temperature increase is just 2 degrees. So I don't think the temperature affect much in our experiment.
But again, average temperature, yeah?
No. Then we can calculate the pulse energy.
Yeah.
The 100 energy pulse energy goes to a liquid. The temperature increase is just 2 degrees.
But over which time? So you deliver energy over 5 nanoseconds, and the temperature increase is over which period?
Just after the pulse.
So 5 nanoseconds later.
5 nanoseconds, yes.
Okay. 2 degrees. Okay, yeah, thanks a lot. That's informative.
Thank you very much. This was an interesting discussion because we have something very similar in mind. But I think temperature is always a big question, and the transients which Johannes asked are very interesting. And the idea of using some proxy, like seeing dielectric constant, something like an indirect measure of temperature, would be interesting. That's really a good idea. I would like to take a few last minutes to ask about, because what I've seen, and I haven't seen it explicitly on a webinar, but I see that conceptually you are considering that electric fields are doing some mechanical stress on protein in general, right? Because you've seen that, and you see that in cells, obviously, also in giant unilamellar vesicles. So this is interesting, and yeah, so that's where it comes into. You mentioned that some proteins you consider to be more soft than others. So do I understand it correctly that you consider the proteins with the more disulfide bonds, SS bonds, are the more rigid? That's the like general idea, right? Yes. So that's okay. Okay, I will double check it. That's how you perceive that. And okay, I see also there is a question from Tomasz Zakar here. So Tomasz, I'll unmute you so you can ask yourself. Just give me a second. I have to find you in the list of participants. Okay. So Tomasz, you have the mic allowed and also camera if you like.
Hello, can you hear me?
Yes.
Perfect. So thank you again for this excellent talk and very interesting talk. I would like just to ask if, I'm just wondering if you tested different ionic or any other chemical concentration like low ionic or high ionic concentration when you applied poses for those artificial cells regarding with this the 12th slide of yours.
Okay.
Like, have you tested the different ionic concentrations or any other?
I see. Yes. This is theoretically can be explained. Okay. I'm going to share that slide.
Perfect.
Right?
Exactly. Yes, this one.
Yeah. This is in this case the conductivity. The deformation depends on the conductivity, intracellular conductivity and extracellular conductivity. The relation. In our case, in this case, the extracellular conductivity is higher than intracellular conductivity.
Mm-hmm.
In this case, the cells are pushed in the direction of the electric field.
Okay.
On the other hand, the extracellular the conductivity is lower than the intracellular conductivity. The phenomena is opposite. The cell forms is extracted. I don't know how to say English. Anyway,
it's expanding in
the direction of the electric field. Yes.
Okay.
Yes.
I see. Okay. Thank you.
Thank you very much for the question and answer. So I think we are almost over time. So I understand. So now that you have to run, or
Oh yes,
for the other meetings and duties. So there are I have also got other questions left, but maybe we can organize something separately. And yeah, I would like to thank. So I would like to conclude that this interesting webinar, for interesting talk and discussions. So that's very great. So I would like to first thanks to our speaker, Dr. Sunao Katsuki, for his time and for very interesting lecture. Again, I apologize for the unexpected technical issues we had, but we managed to overcome that. And I also thank very much to all the attendees and very rich discussions we had this time. So with this, I'm stopping the recording.